Okay, welcome. How are we doing today?
We are doing good.
Good. Hot in here.
I'm going to be here.
So, homework due Wednesday, quiz Wednesday, don't forget. You guys know the drill. So we're going to move on and we're going to learn how to use those eigenvectors and eigenvalues today. That's actually, so this week we're going to be all about applying that to state equation diagonalization, finding the state transition matrix, solving problems. The first homework's pretty easy. The second homework is also in chapter 10. It'll be a little bit tougher. So we'll just get going. So it's useful to transform a system's state vector x into a special basis that diagonalizes the A matrix. For systems with n distinct eigenvalues, this is always possible. In a diagonalized form, it will be relatively easy to solve for the state transition matrix. So I told you that we were going to come up with an easier way to compute the state transition matrix, phi, instead of going to the definition of the matrix exponential, which I said was not the best way to do it. So we didn't focus on it. This is that way, okay? We're there. So I'm going to start to expect you guys to compute these state transition matrices using this method. So the first thing that we need to learn how to do is to change bases in the state equation, just period. So if we have a state equation, we want to be able to change bases. Now, if you guys are, well, we probably talked a little bit about this, but changing a basis for any vector space, or for any vector, is pretty easy, and we're going to learn how to do that. And we're just going to apply that to this state equation. So, as with all basis transformations, it can be written in the form x equals some matrix, some transformation matrix, times x prime. Okay, so we can solve that for x prime. X prime is our new vector, our new state vector in this transformed basis. So we just inverted p and moved it to the other side, slash left multiplied by p inverse. Either way, 6 or half a dozen. So that is a basis transformation. So you can either go from x prime to x, or you can go from x to x prime, depending on which equation you use, right? Now, they're the same vector, right? They're just in a different basis. So they represent the same thing. So we didn't really lose any information or anything like that. We could always transform back if we want to. And you'll learn more about it in linear algebra if you haven't taken that yet, how to do basis transformations. But I did talk a little bit about it in my linear algebra primer last semester, so you can look that up if you want a little bit of a refresher on basis transformations. Essentially, if you multiply a vector by a matrix, that can be a form of a basis transformation. And that's what we're going to use here. So P, we haven't said what it is, just some transformation matrix. And the x prime vector is going to be in whatever basis that dictates, whatever the P matrix puts it into. Okay? We're going to use a very specific transformation matrix in our problems, but for now we want to be able to learn how to, if we want to change basis, how can you do that in general, not just for the specific case that we want. So this is how you do it in general. We just take the state equation, which is just x dot equals ax plus bu, right? And we just plug in x equals px prime. And we just simplify it down and write it as x prime dot equals whatever the new A matrix is, x prime, plus whatever the new B matrix is, times u. Okay, so that's all we're going to do. It's pretty straightforward, just plugging it in and moving things around. So we're going to substitute this into the state and output equations. In the new basis, it's very easy to show. Now it's x prime dot, because this is the new state vector in the new basis, times our new A matrix is going to be P inverse A, the original A matrix, P times x prime. Okay, plus P inverse times the original B matrix times U. And so we see that this is our new A matrix, so we'll call it A prime. And this is our new B matrix, so we'll call it B prime. And I mean, it's pretty straightforward. All we did was, there was an x here before, right? Before we did the substitution, it was ax. And we just plugged in that x is equal to px prime. So that's where we get the px prime. And there was still the a from before. So it's a px prime. And then from this left-hand side, we took the time derivative of this equation. Of this equation, and this is all constants, so it's just x prime dot, and then the p is out here, so we multiply both sides of the equation by p inverse, and that's where the p inverse comes from. And that's why it hits on this one too, because the p inverse came from this left-hand side, so it has to hit on both. So, pretty straightforward. And then if you just plug in, it's really easy for the output equation. The output equation is not suddenly orange. I like my blue instead. Y equals CP x prime. So notice that x, we just plugged in px prime for x. And that's this original C matrix. So it was Cx, now it's Cpx prime. Plus, and D doesn't actually change at all, U. So if I cared to, I could call this the C prime matrix, and this I could call the D prime matrix. Notice that D prime is just equal to D. So only the A, B, and C matrices change at all. Okay. So that's pretty straightforward, right? I don't know. Do you guys have any questions on that? I know there's a little linear algebra, and it's a little bit scary, but there's nothing here besides just matrix inverses and multiplies. That's it. Yeah?
So what is this x prime dot telling us compared to when we just had the x vector with the state space?
That's a good question. So x prime has to be a new state vector. So it has to be able to describe all the dynamics of the system, just like the original state vector did. So if you know the state at any given time, and you know the inputs, you know everything there is to know about the system dynamically. So this is a different representation. So for instance, if we started out and the two state variables were, say, the velocity of a mass and the force in a spring. So say it was like a spring mass damper system, and it was a velocity of a mass was one of the state variables, and then the force in the spring was another one. You could come up with a transformation matrix, P, if you could contrive one, and there would be one if you could find it, that would transform those two variables into say the position of the mass and the velocity of the velocity and position, or the momentum, or something like that, like two different variables that still captured all the dynamics. So the ones that we choose when we do our linear graph modeling and we choose state variables, those are not unique. They can be really swapped for lots of different options. We choose them because they seem to make a lot of sense to describe the system. And a lot of times, state variables on larger systems, using different modeling techniques, they end up not making a lot of sense. It's like the fourth derivative of something, and you don't know what that means, like physically. So our state variables are nice, and we don't usually want to transform them unless we come to a situation like this where we're going to want to diagonalize. And that's actually what the next step is to choose a very specific transformation matrix P. That very specific one is going to help us to diagonalize the system and find a really nice way to get the state transition matrix.
That's just like identifying other variables that aren't stated in the problem, for example. This P matrix is helping you like define other variables?
Yeah, it would just let you state the problem differently. I mean, so you could just say, okay, instead of velocity of the mass and position force in the spring, I want to describe it as the position of the mass and the momentum of the mass or something. Like those would be two alternative variables that would be totally valid to describe the system dynamics in. And so your new state equation, when you solve for x prime, when you solve this state equation for x prime, you're finding those variables and not the original ones. There's not a lot of reason to do this, though, because we have our output equation. Not a lot of reason to do it if you just want different variables, right? Because if you just want different variables, you can just get them from our output equation if we want. We can choose our C matrix and our D matrix to get out what we want from it. But there are specific cases where it's useful, and this is one of those cases. So when you want to find the state transition matrix, it's useful to diagonalize. So to choose a basis that's going to make this A prime matrix into a nice diagonal matrix. And that's going to be nice for solving the system. Essentially, it's going to be nice for finding the state transition matrix, and if we have that, we have the solution. The state transition matrix is like the key to the whole solution, right? So if we can find that, we can find the solution. Now that solution is going to be in x prime variables, okay? It's not going to be in x variables, but we can, if we know what x prime is, we know what x is because we have this transformation back. So it's really, it's like shifting over. Do you guys remember in differential equations when you learned Laplace transforms?
Yep.
And you guys were like, okay, I'm going to switch over to the Laplace domain and solve it algebraically, and then I'm going to inverse transform into the time domain for the solution. That's like not, it's analogous to what we're doing here. We're not using Laplace transforms or anything like that, but what we're doing is we're saying, okay, there's a convenient way to look at this problem, and it's in terms of this diagonalized system. In this basis, it's easier to solve using the state transition matrix. And we're going to solve it, and then we're going to transform back to the x original basis so that we can know what our solution is in terms of our state of variables that we started with. So that's hopefully becoming more clear. Okay, I think it'll become more clear as we get into it. I'm going to do an example, too. Probably going to be on Wednesday. So modal and eigenvalue matrices. Guess what? We're going to use the eigenvector problem to construct our transformation matrix. Okay, so I just said this is for any transformation P. Now we're going to define some matrices that are going to help us choose a very specific P that we want. Okay, so definition. Let a state equation have matrix A with n distinct eigenvalues lambda I and eigenvectors mi. Okay, so each eigenvalue lambda I corresponds to an eigenvector mi. Okay, we learned how to find those last time. Let capital lambda, so this is a capital lambda, big lambda, be defined as, so it's a matrix, and it's going to have the eigenvalues along its diagonal, okay? So all the way down to lambda n, and everything else is a 0, okay? So everything else is a 0. But on the diagonal, we have the eigenvalues. There are n eigenvalues, so it's going to be, n of them along the diagonal. Okay. We call this the eigenvalue matrix. It kind of makes sense. We use capital lambda for the matrix, little lambda for the eigenvalues, and they just go along the diagonal. Okay. Interesting fact. Well, I'll wait till after this. So furthermore, let m, capital M, be defined as. So m is defined as. And now I'm going to use this notation. I'm going to write a matrix, but I'm going to put vectors in it. So this is a notation you probably haven't encountered yet, but not to worry. It's pretty straightforward. So m1, m2. So these are the eigenvectors that we're putting into this thing. And so all the way down to mn. So these eigenvectors, we'll represent them as column vectors, okay? And so if you put a column vector in here, it takes up a column of the matrix. And then these little separators are just supposed to denote that. You're putting in a vector as a column, and then the next vector is the next column. And so we have here another n by n matrix, okay? There are going to be n values in each vector, so each column is going to have n values, and then it's going to be n vectors. So these are two matrices, the eigenvalue matrix lambda and the eigenvector matrix m, okay? And just to give it away, m is going to be the p matrix. So we're going to use m as our p matrix. And we're going to use lambda as well for something else, and we'll see what that is in a moment. Now, here's the little fact that I brought up a moment ago. MATLAB, if you ask for, so if you have an A matrix and you want to know what the eigenvalues and eigenvectors are, it has a really nice little command, and I encourage you to use this. Has a nice little command that computes the eigenvalues and the eigenvectors. And the way it returns them to you is as these two matrices, lambda and m. So let's say A is equal to 1, 2, 3, 4, okay? And if we did eig of A, I have to do, it only returns the eigenvalues if you do eig of A. If you do, let's see, help eig VD. So they call the eigenvector matrix V in MATLAB, but I'll do M, and I can't do a lambda, so I'll do L equals eig of A. And M is the eigenvector matrix that came out, and L is the eigenvalue matrix that came out. So pretty sweet. I totally recommend that you learn how to do this. I mean, it's really, that was the whole thing. That's all there is to it. But I encourage you to learn how to do it in MATLAB and learn how to do it by hand, at least up to a 2x2. Well, probably 3x3 would be best, but at least to a 2x2 for exam purposes. Okay, so that's how you find lambda and m. pretty easy. I mean, so you find the eigenvalues like we learned how to last lecture, stick them in here. Find the eigenvectors like we learned to last lecture, stick them in there. Alternatively, you can check in MATLAB what they are by using the eig command. Okay, now we're going to use this. So I just defined what they were, lambda and m. But now I'm going to use m as my transformation matrix. Now it's not immediately obvious why I'm using m, but it'll become obvious in the end. I hope it's obvious. It's kind of cool. So let x prime equal m inverse x. So that was just using m as our just p transformation. Okay. So as long as there are n distinct eigenvalues, m is invertible. We are going to use only that situation. In this class, we're not going to consider the possibility where there are not n distinct eigenvalues. It's not that hard to deal with, but it's just one more thing. So where m is the modal matrix, so we call m the eigenvector matrix or the modal matrix for reasons. So modal is a nod to like vibrations concepts, which you haven't learned yet, but there are different modes. So you've learned in physics, you guys learned about modes. So like a string, you guys probably saw a string vibrate at its natural frequency, and you can actually see that happen. And depending on the length of the string and other parameters, you can get different modes to be excited, right? And that is where that concept of modal matrix comes from. It turns out that eigenvectors and eigenvalues are very related to those sorts of modes. And we'll talk. Maybe we'll do an example where we do a small vibrations problem. Might be fun. So lots of applications of this, but we're just going to focus in on the broad theory for now, and it has lots of different places we can apply it. We'll apply it certain places in this class. In future classes, maybe in vibrations, you guys will talk more about modes. Okay, so if we just plug in x equals mx prime into the state equation, we get this. Okay, that looks exactly like this, except for wherever you see a p, there's now an m. Okay, so we've got this. So here's the thing: this m inverse am thing is kind of this is sort of the big move that we make here. There's this sort of trickiness that ensues in this little step here, and I'm going to try to bring you along with me. So let's say we wrote am, which is just the rightmost terms of this expression, right? And we set it equal to, and then we leave a little bit of space because I'm going to insert something there, is equal to m lambda. Okay, that was a very poor lambda. Well, that was really poor. It's getting worse. I'm going to leave it that one. It's not very good. So m lambda. So I'm asserting that this is an equality, okay? This is true, but it's kind of hard to see it at first. So let's remember what m is. M is comprised of these vectors, these eigenvectors, right? So if you consider each column separately, which you can do, you can think of this as each column separately. You can say A multiplying the first column of m, which is m1, the first eigenvector. That has to be equal to, if you take the first column of m1 here and multiply it by lambda, okay? That's something that you may not be familiar with from matrix algebra, but it's true. And if you do that, what you end up with is it's just an eigenvalue eigenvector problem. It's just the A matrix times an eigenvector equals of essentially a scalar scaling the vector. Okay, so that scaling of the vector being equivalent to a matrix multiplying the vector. That was what the eigenvalue eigenvector problem was. And since we have these eigenvalues and eigenvectors plugged in, this equality is valid. So I know that is a little bit of a leap, or it's a little bit fuzzy, a little bit hard to see, but it is the case. Then what's kind of cool is M inverse right here. If we add that term, we have to add it to both sides, right? M inverse. So this right-hand side can now be simplified, right? What is M inverse M? Just the identity, right? And so we can just write lambda. So M inverse AM is just equal to lambda, the eigenvalue matrix. So that's pretty sweet, because we can now write our new transformed state equation as x prime dot equals, instead of M inverse AM x prime, we can just write lambda x prime plus it's M inverse B. I'm only putting parentheses around these terms just to show you, oh, this is the new B matrix. And y is equal to, the C matrix changes by multiplying the original C matrix by the modal matrix M x prime plus just the original D matrix times U. Okay? So recall that lambda is completely diagonal. And so this is our diagonalized form of our state equation. And this lambda, I know that the derivation might have been a little bit hard to follow, but what's nice is once we've done it now in class, we don't have to do it again every problem. We can just say, oh, if I want a diagonalized form, all I need to do is find my eigenvalues and my eigenvectors, and that defines big lambda and big M, right? And then I could just use this formula, this expression here for the state equation, this one for the output equation, and I'm done. So it's pretty sweet. So I used MATLAB to do the little eig of A situation here, and I define M and L. So let's take a state matrix A, and let's take that state matrix A, and let's diagonalize it. Let's see if this actually works. So I said that M inverse AM should be equal to lambda. So let's see if that's true. In MATLAB, we can just check super easy. We don't have to do all the stuff by hand. So let's just see if matrix inverse is inv, right? INV, yeah. M, and then times A times M, right? So we're expecting to see L come out, right? The lambda matrix. So let's see if I'm just blowing smoke or not. I did not try this before. We will see. Oh, it worked! Yay! The world makes sense. So we see that there are zeros except for along the diagonal. And we see that this is lambda 1, and this 5.37 is lambda 2. Yes?
Those are our eigenvalues, correct?
Those are our eigenvalues, yes, along the diagonal here. So, I mean, when you have MATLAB, I mean, doing this is super easy. Computing lambda and m and all that stuff is super easy. But you don't have to do this every time. You can just know, oh, that new A matrix is just going to be lambda. Now, probably it's good to check if you've got, a computer handy. It's good to check that your m and your lambdas are all consistent, and that you get the right thing out. So this was like a check that we can do. So it's fun. So, all right, how do we feel about that? As excited as Niles is when I toss his little green chew toy bone across the room.
No, not that.
He gets pretty excited. Sometimes, like he'll run after it and he'll bring it back. He learned sit really well yesterday. He still knows it today. And I was like, I don't know how the retention's gonna be, because yesterday he was like sit, Niles. It was like bam. Well, when he feels like it. He definitely knows sit. He just sometimes chooses to just continue to be rambunctious. Okay. So here's an easier way to compute the state transition matrix. Recall our definition of the state transition matrix. Phi of t is equal to e to the AT. Now, directly applying this to the diagonalized system, because our new A matrix is just lambda, right? So phi prime is equal to e to the lambda t. Now, here is a property of matrix exponentials that you may not know, okay? If you take the matrix exponential of a diagonal matrix, it's really easy to compute. It turns out that all you have to do is plug in a regular old exponential to each of the diagonal terms. So the first one is e to the lambda 1t. So then the next diagonal term is e to the lambda 2t. And then we go all the way down to e to the lambda nt. Okay? So that's pretty sweet. And then everything else is 0. And that's our state transition matrix in the primed coordinates, okay? So remember, if we have phi prime, we can find the homogeneous or unforced solution immediately, right? And when you multiply a diagonal matrix by something, so this is phi prime times the initial condition, you just take the initial condition in each variable and you multiply it by e to the lambda 1 or 2 or whichever term it lands on t. And so we have the initial condition of the primed state variable x1 times e to the lambda 1t. So notice, if you don't, so say you put, what if you put 0 in as your initial condition in, say, x1? Would that term contribute anything? No. x2, would that term contribute anything? No. So your initial condition, essentially, what they call it is excites only the one mode, okay? This is what's sort of physically significant about eigenvalues and eigenvectors, is that each eigenvalue corresponds to an eigenvector. And we call that a mode, okay, the modal matrix and that idea. If you have no initial conditions in that mode, nothing ever happens in that mode. That never gets excited. There's 0 contribution. So which is pretty cool to think about. So let's think, so for instance, we haven't talked much about this, but the equivalency of the roots of the characteristic equation and the eigenvalues that we drew earlier, we said that they were equivalent. Do you remember that the roots of the characteristic equation, if they had negative real parts, they were stable, right? If they had positive real parts, they contributed an expanding exponential, so it was unstable, and then there was the marginally stable with 0 real part. So that still holds true. So notice that, so lambda here, if it has a positive real part, it's going to be unstable, right? If it has a negative real part, it'll be stable. So technically, you could have an unstable mode in your system. Say it was lambda 1. It was equal to like 4.2 plus 0.6j or something like that. So it was complex root. It has a positive real part. But if you didn't excite that mode, if you just said, okay, no initial condition in that mode, the system would still be stable as long as the other modes are stable. So if you never excite an unstable mode, it never goes off to infinity, which is something you have to really watch out for, because if you're not careful, you can do that. You can just not excite an unstable mode. But real systems that have an unstable mode always are going to get excited in that mode. There's always going to be a little bit of a perturbed variable or value at some point that'll start it off to infinity. Okay, so it's important to keep in mind that we can do things analytically that appear, oh yeah, no, it's fine. We'll just never excite that unstable mode. But in reality, if we have this system, it will get excited, and you have to be careful when you're analyzing systems that you don't forget that. Okay, so our x prime of 0 is we just have to transform our initial conditions as well, right? We had to transform the state variables, but also the initial conditions, which makes sense. Okay, recall that x homogeneous of t is equal to phi of t times x naught, so the initial condition. What we want is to be able to express x homogeneous of t in the unprimed, in the original state variables, right? So it's great if you solve this in the primed variables, and you could just go ahead and do that all the time. But sometimes you want to know what it is in terms of the original state variables. And so sometimes we'll work in all primed coordinates, and then at the very end we'll convert our answer, or maybe at some point we want to transition back. So let's convert it sort of in the midstream here. So if we say x homogeneous of t is equal to, so using this, if we transformed our initial condition first, let's do that. So we'll use our phi of t times, and then I'm going to use this expression right here. So I'm going to say x of 0, the initial condition in the unprimed coordinates, is just equal to m times x prime of 0. Okay, that's just a transformation of the basis of the initial condition, right? And now I'm going to left multiply both sides of this. Well, actually, no. I'm going to transform this x homogeneous into primed coordinate. So that's easy enough to do. We go back up to way up here. We have this relationship, right? So we can use that on the left-hand side. And we can say that m x homogeneous prime of t equals, same thing on the right hand side, phi of t, m x prime of 0. Okay, so that implies, so you can left multiply both sides by m inverse, which would get rid of this one, and would leave x prime homogeneous of t equals, and then it's going to be m inverse phi of t m x prime of 0, which leads to, and all of these things. So I'm just going down, and then I'm going to go up to the next column. I'm going to say that this right here, this is in the exact form of a state transition matrix, right? It says x prime homogeneous is equal to some matrix times the initial condition in the prime coordinate. So we're going to actually just call that phi prime. We never defined a phi prime, but now we have. So now we've got this expression here, phi prime of t equals m inverse phi of t m. Okay? And how did we come up with that expression? Where did we come with that? So that what this said is that phi prime is equal to, so you could write this as an equation, right? Which is what I did. I said phi prime is equal to m inverse phi m, which is exactly what we did here. I mean, I just defined phi prime to be this, but in fact, phi prime was right here. I mean, this was phi prime that we've been working with, right? But we just related it to the original phi, which is what we needed. We wanted to know the relationship between phi and phi prime, and here's what it is. So if you found phi, or if you found phi prime, you could transform one into the other using this equation. And the way that we're usually going to want to go, because phi prime is easy to compute, right? But we often would like to know what phi is. So you could do all of your solutions in the primed coordinates and at the end transform, or you could say, okay, I found phi prime, I want to do the rest of it in my original coordinates. So transform it back to the unprimed coordinates, and you get m phi prime of t m inverse. Okay. So this is, here we go. Finally, this is the preferred. I always forget, it's just one F, yeah. 2 R's, preferred method of finding phi. So instead of trying to go to that Piano-Baker series definition of a matrix exponential, instead what we do is we come here, we find phi prime, and then we plug it into this expression. In order to find phi prime, remember we had to find lambda, big lambda, all the eigenvalues, and big M, the modal matrix, all of the eigenvectors. And then it was straightforward to find phi prime actually, once we just found the eigenvalues, we knew phi prime. You do need to know the eigenvectors if you want to transform it back into phi, though. So it's pretty straightforward. I'm going to do an example on Wednesday of this, and you'll be having homework over it. All right? Have a wonderful day.